Welcome to the pre-lecture for Class 21.
Today we'll focus on how to carry out a local stability analysis.
Let's go to the first slide. First, a brief review. We know what the equilibrium points of an ordinary differential equation system are. They are those points that make the derivatives vanish. Now note that if we have a homogeneous system of ordinary differential equations, then the zero vector is always going to be an equilibrium point, and in fact, it will be the only equilibrium point. If your initial condition is also the zero vector, then the solution will be zero for all time. Now let's talk about defining stability properties. These are very similar to what we saw in the linear cases, but we have to be somewhat more precise in the nonlinear cases. An equilibrium point is said to be stable if for all positive numbers epsilon that are small, there is a delta such that for an initial condition,
X naught delta close to the equilibrium point, the solution X will remain epsilon close to the equilibrium point
for all time t. That's the formal mathematical definition. In plain English, that means that if you start close to an equilibrium point that is stable, you will stay close to that equilibrium point. Now, what does it mean to be asymptotically stable?
This means that if you start within some neighborhood of the equilibrium point, then all solution trajectories are actually going to be drawn to that equilibrium point over time.
In plain English, that means that not only is the equilibrium point stable, but it is also attracting. So to compare what it means to be stable versus asymptotically stable, a stable node,
a stable spiral,
or even a center are all examples of points that are stable. On the other hand, to be asymptotically stable, that equilibrium point has to draw solution trajectories in toward it. So the stable node and the stable spiral are still asymptotically stable, whereas the center is not considered asymptotically stable, it is simply stable.
Now,
what does it mean to be neutrally stable? It simply means that we are stable, but not asymptotically stable. So that's basically the case of a center. And finally, to be unstable, it just means that the point is not stable, so it doesn't fit into any of the other categories. So in plain English, it means you can start close, but you are going to get pushed far away
as time progresses.
So an unstable point is considered a repelling point. An example would be an unstable spiral or a source, or an unstable node. Let's go to the next page and look at an example.
Here we have examples for which we have already created
the phase portraits of the ODE systems and inferred what kinds of equilibrium points we thought we might have. So for example, for this first nonlinear system, we found two equilibrium points. One was located at -1, 0, and one was located at 1, 0. From looking at the solution trajectories, the -1, 0 equilibrium point looks like a saddle point, while the 1, 0 equilibrium point looks like an unstable spiral or a spiral source. Let's look at another one of the examples we did last time, the interacting species model. This one had 4 equilibrium points. We can see that 2 of them look like saddle points. And then we have 2 others. One at 0, 0 looks like a stable node, and the other looks like a stable spiral. In each of these cases, we can see intuitively what we think these points are, but what we're going to learn today is how to do a local analysis to confirm what we are seeing with our eyes. Let's go to the next page. So now we're going to get into the details of how to do a local stability analysis. Let's just remember that with the phase portraits we have seen, we did find what appeared to be saddle points, nodes, spirals, and centers. We can show mathematically what kinds of equilibrium points those really are. This is called a local stability analysis. It gives us qualitative information about the behavior of the differential equation solution trajectories near the equilibrium point. The main idea behind this analysis is to use a higher dimensional Taylor series expansion to approximate any nonlinear differential equation system near its equilibrium point as a linear system. When we do that, we can make use of everything we learned about linear constant coefficient homogeneous systems of the form x prime equals ax. Let's go to the next page for a lower dimensional idea of what that means. Let's just briefly review what a Taylor series expansion gives us. The question here is, what is the linear approximation of the function sine x at the point x is pi over 3? Take a second, pause the video, and work this out yourself. In addition, I've provided a plot here. Label the parts of this plot that highlight how the Taylor expansion can be an approximation to sine x. Okay, let's look at the Taylor expansion around x is pi over 3. If we take sine x near pi over 3, that is going to be approximated by sine pi over 3 plus cosine, first derivative, evaluated at pi over 3 times x minus pi over 3.
And
that's the first linear term. We'll stop there since we're just looking at an approximation. And when we plug in those values, that gives us root 3 over 2 plus 1/2 x minus pi over 3. Now let's label the relevant parts of this plot. Of course, we have the x-axis and the y-axis. The blue curve is our sine x curve, and the orange dotted line is the linear approximation to sine x near pi over 3. So it is the line root 3 over 2 plus 1/2 x minus pi over 3. Now let's look at what's happening near pi over 3. Not only does the line approximating sine x intersect with the plot of sine x itself, but near pi over 3, we can see that the straight line approximation to sine x is a pretty good approximation. In other words, as long as we don't move too far away from x equaling pi over 3, we can simply approximate sine x by using the straight line. Now let's go to the next page to extend this idea to higher dimensions. Here now is the process of carrying out a local analysis of an ODE system near an equilibrium point. Let's suppose we have an ODE system, x prime is some vector of values, f of x, and that there is an equilibrium point at the point labeled x sub eq. Now, by Taylor's approximation, we can expand the derivative of x prime, which is f of x, in the following way. We evaluate the vector function f at the equilibrium point x sub eq, and then we take the Jacobian matrix evaluated at the equilibrium point x sub eq times x minus x sub eq, and so forth. So this is the first order approximation. Notice a couple of things. By definition, f evaluated at the equilibrium point is going to have to be 0. So the first term we're left with is this Jacobian matrix term. The Jacobian matrix is simply a matrix of partial derivatives. Now, writing this in somewhat more familiar terms, let's define y to be the difference between x and its equilibrium point. We are effectively shifting the system back to having an equilibrium point at 0 or at the origin. Now, when we take the derivative, we can see that y prime can be approximated by a matrix times the vector y, where that matrix A is the Jacobian matrix evaluated at that equilibrium point. What is this telling us in summary? It is telling us that near the equilibrium point, a differential equation system is going to behave very similarly to the linear system of equations approximated by y prime is ay, where A is the Jacobian matrix evaluated at that equilibrium point, which means we already have all the tools we need now to understand the behaviors of every equilibrium point in a nonlinear system by using the knowledge we've already built
for
linear systems. For notation, let's just remember what that means to create a Jacobian. So f is a vector-valued function, and its components depend on the independent variables x1 through xn. Let's keep in mind that the vector function f can be written in its component form as f1 that depends on x1 through xn, all the way through f sub n that depends on x1 through xn. So the Jacobian itself can be thought of in a couple of ways. First, we can think of it in terms of column vectors in a matrix, where each column is the derivative of our vector function f with respect to each independent variables subsequently, x1 through xn. We can also think of this in terms of rows, where each row of the Jacobian matrix is the gradient of the ith element of vector function f. Finally, we can also just think of the Jacobian as the following n by n matrix. Whichever perspective helps you remember this the best is the one you should hang on to. Let's go to the next page now and look at an example of how to make use of the Jacobian to determine the stability of the equilibrium points in a system. This is one of the systems that we looked at previously, where we plotted the phase portrait, and we found two equilibrium points, one at -1, 0 and one at 1, 0. We're now going to do a formal analysis of the stability of each one of those equilibrium points.
So let's first
Write the system in vector form, where this right-hand side is now our vector function f. On the left here, let's write down what the Jacobian matrix is in general for this system. Now, plugging in the particular values for the function f, we have the following Jacobian, noting that partial f1 partial x is the partial with respect to x of -y, and that gives us 0 in the 1, 1 entry, and so forth. Now, this is the Jacobian no matter which equilibrium point we are looking at. But since we have two equilibrium points, our next step is to plug in the values of x and y at each of these equilibrium points and determine what kind of equilibrium point we have that depends on the Jacobian. Let's first note that standard notation for the Jacobian is the derivative of the vector function f. So now if we're going to evaluate what that Jacobian is at the equilibrium point -1, 0, we can write the Jacobian at -1, 0. Plugging in those values gives us 0, -1, -1, and then the only value that's going to change is the one that depends on x. And so that is going to be -2, because x has value -1.
Now, the behavior of our nonlinear system can be well approximated locally by this Jacobian times vector x.
Now we can use this Jacobian for our linear analysis. We can either look at the trace and determinant, or we can find the eigenvalues to tell us what type of equilibrium point -1, 0 is. In this case, I have eigenvalues -1 and 2, so one is negative and one is positive. This immediately indicates that this equilibrium point is a saddle point. Let's next look at equilibrium point 1, 0, and we'll label that B. Here we start with the same Jacobian, but now evaluated at 1, 0, which is going to be the same matrix except in the 2, 1 position, where now, since the value of x is 1, the value of the 2, 1 entry is 2. In this case, the eigenvalues of the associated characteristic polynomial are going to be complex. Since we have complex eigenvalues, we know we can expect spiraling behavior, but will it spiral in or out? As we've done before, let's look at the real part of the complex eigenvalues, and what we see is that the real part is positive, indicating that this is going to be an unstable spiral. I hope these computations make sense, but the next question you should be asking is it valid to do such a thing? And it turns out that there is a theorem that tells us exactly when we can carry out such a linear analysis and when we need to be more careful. So let's go to the next page and talk about the Hartman-Grobman theorem. This is an important theorem that tells us that the linearized analysis we are doing is going to be valid in many of the cases we're looking at. So let's suppose we have an equilibrium point that we've labeled x sub eq, and we're looking at an autonomous ODE system. As long as the associated Jacobian matrix evaluated at that equilibrium point has no eigenvalues with 0 real part, then we can say that the linearization is faithful with respect to stability. So in other words, if all of the eigenvalues of our Jacobian evaluated at that equilibrium point have negative real part, then we can safely say that that equilibrium point is asymptotically stable. On the other hand, if any of the eigenvalues of our associated Jacobian at that equilibrium point have a positive real part, then we can say that the equilibrium point is unstable. Now, there are a couple of things to note here. First, if even one of our eigenvalues has 0 real part, and if even all the rest have negative real part, the stability of that equilibrium point cannot be determined. That zero really throws a monkey wrench into the works. We cannot use local stability analysis alone. We have to do something else, which we will be talking about next week. So in order to have that stability, we need all the eigenvalues to have negative real parts. The other thing to note is that the linearized system, the one that comes from looking at the Jacobian at the equilibrium point, is going to have the same type of equilibrium point as the original nonlinear version, except when the linearized system has a zero eigenvalue or repeated eigenvalues. So again, unless we are running into that exceptional case with a zero eigenvalue or repeated eigenvalues, we can be confident that our linearized system is a good reflection of our nonlinear system. Many of you are probably asking yourselves, then what do we do in those cases? And that's what we're going to talk about next week when we deal with Lyapunov functions. Now, just so we understand this a little better, why does that zero real part make a difference? It's very related to the second derivative test from calculus and why that fails if the second derivative is zero. Think, for example, about the function f of x is x minus a to the 4. We know already that the first derivative at a is zero. And the question we ask is that critical point going to be a minimum or a maximum of the function? The second derivative test is going to give us the answer to that. If the second derivative is positive at the point A, the function is concave up and we have a minimum. If the second derivative is negative at the point A, the function is concave down and we have a maximum. If, however, the second derivative is zero at the point A, we cannot use the second derivative test. It does not give us any information. And when we think about the Taylor expansion, we see that the first derivative is going to be zero, but if the second derivative is also zero, we are losing important information and we have to do a little bit more analysis. Let's go to the next page for a handy chart. This is a table that connects the linear to the nonlinear system analysis that comes from the textbook by Borelli and Coleman. These were former Harvey Mudd math professors. They've used slightly different notation from what we have used here, but what we can see is we are looking at a linearized system where A is in fact our Jacobian matrix, and that is approximating our nonlinear system where we do have some remainder term from the Taylor series. For this particular chart, we're looking at a matrix that is a 2x2 matrix of real numbers. And the table is only going to show the asymptotically stable, neutrally stable, and saddle cases. So they do point out that if you have a case where the real parts of both eigenvalues are positive, simply reverse the arrowheads and you can label the portraits as unstable. They also point out that the case where an eigenvalue is zero is not part of this table and has been left out because further analysis is required. As we look at this table, if our linearization tells us that the linear system is a stable spiral at the equilibrium point, then we can be sure that the nonlinear system was also a stable spiral near that equilibrium point. And you can go through this table and see how all of these things compare. So for example, if we look at the case of two negative real eigenvalues, we may have a star node or an improper node in the linearized case. And in the nonlinear case, that will have come from also star nodes or improper nodes, but there is a possibility that we also had a spiral. So we can see that there is a little bit of wiggle room. However, the stability characteristics still remain in both of these cases. One other exception that I will point out is if in our linearized case, we have what looks like a neutrally stable center, then it is possible that in the nonlinear case, we also had a neutrally stable center.
But the catch is that
we cannot necessarily be sure of either the orientation or whether that center, in fact, came from some kind of spiral. And here's the kicker, that spiral could also have been either stable or unstable. So in the case of a neutrally stable center, notice what's happening is we have zero real part to our complex eigenvalue. And that's why a little bit more analysis will be required. Again, this is something that we're going to talk about more next week. Finally, in the case of a saddle point, we can be assured that a saddle point in the linearized system is a saddle point in the nonlinear system. Okay, that is it for now. When we meet in class, we are going to get to practice doing some of this linearization local analysis on a couple of different systems. I'll see you there.